That's where I jump in. Anybody not heard of NVIDIA before? All right, excellent. I always like that. No hands go up means our marketing guys are doing a good job. How many of you have done CUDA before, worked in CUDA before? Well, about 2 or 3 of you. All right, so this first presentation is mostly going to be about what is GPU computing, why is it important, especially in the the HPC space, and then a little just actually dive into a bit of a technical. We'll show you some CUDA C. It'll take a quick turn just so you can see what it's like to program. It's not the only way to program a GPU. It's just one of the options out there, and just kind of show you what it's about. And then my second presentation, it's open for debate if you guys want to hear about something else, but I'll talk about our recently announced CUDA 5 that we announced last year, and then what our latest hardware is capable of. Our latest, called Kepler is the family, and then the latest chip is GK110, which is coming out end of this year. So just kind of some of the features we've added to it. Any questions so far? All right, good. Feel free to ask questions anytime, very informal. Jump in. If I say something stupid, please yell at me. I've had plenty of, I have some medical examples. I've had doctors yell at me saying, wait, that's not right at all. So by all means. So 3 things I want to, this first presentation, I want to get across to you today. The first one is that conventional CPU computing, especially in supercomputers, has hit a brick wall. Things just aren't getting faster. Why is this? The second one is that heterogeneous computing, hybrid computing, GPU computing goes by many names. It's kind of our way past this wall. And then finally, my third point is that CUDA is an easy way into this future of parallelism with using accelerators or GPUs, as people call them. Now I'm an animated learner, so I animated these 3 points. My first one, CPUs have hit a brick wall. That took me like 20 minutes to figure out how to do. The future is parallel. I realize it's starting to date myself when I talk to undergrads because they don't recognize this car. It's the DeLorean from Back to the Future. They're always just like, I don't get it, which kind of makes me sad. If you're not careful, you're going to get left behind. The future is parallel. And finally, with CUDA, it's a nice, easy ride in the future. So those are my 3 points. All right, Moore's Law. Who wants to take a stab at what Moore's Law is? I assume you guys all know this. Somebody wants to be brave. I normally have T-shirts, but I ran out, so I apologize for that. Anybody? Moore's Law? Go for it. Excellent, good. I usually burn people on that one because a lot of people say speed. The computers double in speed every 2 years. Unfortunately, anything that's exponential in the computer industry is attributed to Moore. My favorite quote of his is, if Al Gore invented the internet, I invented the exponential. Because basically anything exponential rate to say, oh, that's Moore's Law. But no, it's actually the number of transistors doubles every 18 months to 2 years. And we've done a great job of keeping up with this, last 40 years. And we don't really see this slowing down. The chip we released in March was 3 billion transistors. The one coming out then this year is 7 billion transistors. It keeps going up. And at least in the next 5 to 10 years, we don't see this slowing down. But then we have this graph, which is related to this, but not equal. This is just clock speeds over time. And you can see we were doing a really good job keeping up with Moore's Law, but then last decade or so, it's just hit this brick wall, like somebody throwing the handbrake and hockey stick. So why did this happen? What's going on here? Buying computers 10 years ago, it was all about who has the most gigahertz, who can run the fastest. Now it's who has the most cores or other features, because everybody's caught up with each other as far as speed. So it's really 3 different components that make up this brick wall, as I call it. First one's power. Obviously, we're getting smaller and smaller. Intel's at 22 nanometer. We're at 28 nanometer, but we're getting more and more transistors. So, as we drive electricity through these things, they generate heat, and we got to pull that power away. But now we have a much smaller space to pull power away. I don't know if you've ever built computers, but if you forget your thermal grease, forget your heat sink, try to overclock too much, bad things happen. You get that horrible smell, that little puff of smoke. When I was in high school, I did this, man. It just crushed me because it's like a summer's worth of money gone down the drain. But you just can't just keep pushing power through silicon to get it to go faster. At some point, you're going to hit a limit. In the last 20 years, we've gone up a factor of 4,000 in clock speed. So you really got to hand it to the materials and these mechanical guys designing these heat sinks to keep pulling this heat away. But we're frankly just running out of scalable solutions. I don't want to have to top off my computer with liquid nitrogen when I want to play the latest game or do some research or something. It's just we just can't keep pushing faster because we can't pull the power away. Next one's memory wall. This is really the easiest of the 3 to explain, but it's also one of the biggest problems. And this graph just kind of explains itself. Basically, processors, not just CPUs, GPUs, and anything in general, has just been a victim of their own success. This is kind of the Wile E. Coyote Roadrunner analogy. No matter how hard memory tries, it just can't keep up with the processors. And this is definitely not for a lack of trying. I see a lot of people see this graph and say, well, let's just fix memory, and that'll help our problem. But a lot of smart people are trying to get memory to go faster. But if you can't get data onto the chip, there's no point in going faster. There's nothing to work on. So data movement is a really big problem we have in the industry. So that's the second wall, and the third one is instruction level parallelism. Anybody want to guess what ILP is? Anybody? Come on, somebody's got to know what ILP is. Nobody? All right, in the back.
It's when you can actually examine and potentially execute in parallel multiple independent instructions in the processor.
Correct. That's a good answer. Yeah, it's as I put it. I'm a software guy, so it's the hardware guys trying to make my code go faster behind my back to parallelize my code for me. It's essentially, like you said, it's looking ahead, seeing if it can do preemptive work. Trying to guess which branch you're going to go down to, or it says part of my chip's idle. I can do some work ahead of time. It's really useful stuff. We've been relying on this pretty heavily for the last few years to keep pushing our processors faster, and our same serial code can get faster because of this. So why is this a wall? Well, the problem is we have been very reliant on it. First, it's really hard. You're basically trying to predict the future in hardware. This is all hardware done. They've tried this compiler-based. It doesn't work very well. So to this date, most CPUs do this in hardware. It's also extremely complex. If you look at a die breakdown of a modern CPU, a huge portion of it is just control. And we're kind of hitting that crossover point where we have more control logic than we have transistors actually do the work. And so, it's over a quarter now of a CPU is just pure control logic to do all this stuff for us to get stuff to go faster. So we just can't rely on this anymore to keep pushing speeds through processors. So those are our three reasons why, or three of the main reasons why you don't see CPUs just getting much faster anymore. So what are we going to do to get by this? Well, unlikely hero. This is what happens when you give marketing a die shot. They put all this color in there. It doesn't actually look like that when you look at it. It's not very colorful. This is the GPU. This is what it looks like on the right as you buy and say Best Buy. This is what we call an add-in card where you actually just slot it into the PCI Express. This is what it looks like, just like a CPU. You guys can pass this around. This is our latest GK110. It doesn't work, so don't worry about stealing it. This is what most people think of, what you probably put in your servers, or in supercomputers would be some version of this. So why is GPU our answer past this? Why not the mouse or the hard drive or the modem? Why did the GPU suddenly become this powerhouse to help us go move into this future? And it's really games. This is a rendering from Battlefield 3, a modern game. When I first saw this, I thought this was just a picture of a guy in the desert. It's actually a screenshot from the game. And it's because of this. Wolfenstein, great game. This is where I got into gaming. I'm still a big gamer. I enjoy it. A lot of people realized that gaming was a lot of fun back, what was this, 2 decades ago now? And so with all these gamers, they really like the game, but these are honestly crappy graphics. Back then they were pretty revolutionary, but people wanted more really quickly, and a lot of people wanted more. And so this really drove the gaming industry to what it is today. And in 2015, it's estimated we would be about a $25 billion a year industry just for PC gaming. And that's, at this point, we're outpacing, Hollywood. Like Avatar came out, it was 300 million on opening weekend. When Battlefield 3 came out, it was like 700 million for the first weekend selling the game. So these games, a lot of the PC games, $60, $70 per pop. That adds up. And with that, that much money becomes a lot of competition to get that piece of that pie. And with that much competition, drives innovation. When Wolfenstein came out, there were about 30 graphics companies developing different kinds of chips, and now we're down to basically 2, AMD and NVIDIA. AMD bought ATI, so we still call them ATI, but they merged. So only really the 2 left driving these high-end graphics for gaming. On the HPC side, Intel has now jumped into the arena with what they call Mike or Xeon Phi, I think is their actual product name. They tried for a while with what was called Larrabee to be an actual discrete graphics card. That got scrapped, but they've converted that now into what's called Mike. But with that innovation, really brought us to where we are today. Super lush, amazing graphics. I encourage you, even if you aren't a gamer, just to go watch somebody play a game on a high-end GPU with the latest game. It's ridiculous how far they've come, and actually I have a video I'll show you here shortly, because no NVIDIA presentations right without a game demo. But if you just think of Don here in the upper left, this is obviously a scrunched image, but there are millions of pixels in that single image. And each one of those pixels has to be perfectly colored, perfectly shaded to create a realistic-looking face. And then we do it 60 times a second. So there are billions and billions of pixels being processed every second with these GPUs. And it was driven from this innovation to get fast, fluid, lush worlds, and very responsive games, and just no bad graphics. Let me show you this demo here. I apologize, this game's a little violent. I didn't make it. But try to look at this from this prospect of just what's going on. This is all in-game footage. When I was playing games, I always had the pre-rendered cutscenes in the middle of the game, and I always wish I could play in that part of the game. Well, we're kind of now in the future. You're to the point now where you are playing in the cutscene because the hardware has just become so powerful. So like I said, this is actual game footage. Depending on which way you turn your mouse, what you do. Like all the smoke, it is not pre-rendered. This game doesn't support physics, but there's a lot of new games that now have physics built into it. So depending on how you shoot the wall or how you hit a brick or whatever, it's going to break correctly, physically correctly, and then be rendered correctly on screen. All being done on the GPU, both the physics processing and the rendering. So yeah, so that's Battlefield 3. Fun game. All right. So, click. So what is heterogeneous computing? A lot of people assume it's our answer saying getting rid of the CPU. We're not. That's not what heterogeneous computing is all about. It's about using the right processor for the job, using the right transistor for the job, doing what they do best. Heterogeneous computing, hypercomputing is about combining the power of both the CPU and the GPU. CPUs are really good at making single threads go really fast. GPUs are really good at making thousands and thousands of threads in aggregate go really fast. We don't really care about the speed of a single thread. We care about the overall throughput of all those threads, just like a pixel. You don't care about the single speed of a pixel. You care about the thousands and thousands of pixels you're processing a second, or millions and billions of them. And so it's really it's a fairly simple, basic idea. You keep the majority of your sequential code, the stuff the CPU is really good at, file I/O, running the OS, exchanging data with sensors, and you keep that on the CPU. Then you find your compute-intensive, highly parallel parts of your code, and you move those over to the GPU. So now, asynchronously, you can be running stuff on the GPU and on the CPU while they're both doing what they do best. Now, why is this becoming kind of taken off now, just in the last 5 years? Well, basically, if you look at this curve, this is gigaflops per second in double precision, and this is memory bandwidth on the right. And you can see GPUs are faster than the high-end CPU at these types of operations, because these are exactly what are used in graphics. And we're not only faster than the CPUs, we're getting faster than CPUs at this. We're much farther down this exponential curve than the CPUs are. Now, back in 2003, when we were far below this, when we were still on this curve, people like Ian Buck and David Lupke and others saw this trend, and they said, well, I want to get access to the power of that GPU. And so that's when they, at the time, started working on programming these things using like OpenGL. Basically, they hacked OpenGL, and they would feed it in vertex data and then interpret the red, green, and blue data coming out to actually do their calculations. And that's very hard to do. Not many people can do that. And that's where Ian, who invented CUDA, essentially started on this project called Brook in Stanford. And that's where NVIDIA saw that and brought him on. But anybody can throw up graphs, line graphs. I highly encourage you to be skeptical of any line graphs you see. Anybody can fudge their data. So I have some real-world examples of how GPUs are being used today, actually being used in practice. This is CT scans. Everybody's heard of CT scans, I'm sure. This is how you create a 3D image of the body using radiations. Something like 68 million people a year are going to get CT scans. Of course, you're using radiation, which we all know the body doesn't react well to. And there's a group at UCSD that did research on this, and they actually took the data from Hiroshima, how much radiation people were exposed to, and they estimate that about 28,000 people a year are actually going to get cancer from the CT scan. So they may be going in to look at a tumor or whatever, and they're actually getting cancer from it. And they, again, estimate about half those people will eventually probably die from that cancer. So again, CT scans do a lot of really good stuff. 68 million people is a big number, and it saves a lot of lives. But obviously, this is something we want to go after and try to reduce this number substantially. So they've found that by taking very specifically angled pictures, they can create an image, but it's very noisy. It reduces a lot of radiation, but it's not usable. But since they know right where the pictures were taken, they can actually go in with an algorithm and denoise it to actually clean it up so the doctor can actually use it. But using a standard CPU, a high-end CPU workstation, it takes about 2 hours to do a single 3D image. And that's just not clinically practical. I mean, first of all, Google Drive has stopped working apparently. First off, if you want to take one image and then go back and take another, you have to wait 2 hours before you can get a useful image before you even start diagnosing it. If you want to look at a 4D image, like the heart beating over time, that's 2 hours for each of those images if you want to actually reduce the radiation, which, again, is just not clinically practical. So what they did is they went and looked, and they said, oh, this is a very highly parallel problem. Let's try the GPUs. And so using CUDA, they were able to get this down with actually some pretty old hardware. I'm sure this is cut down now, down to 2 minutes per image. And now you actually have something that's clinically practical. Using just a workstation in the doctor's office, by the time the patient's off the table, you have your first 3D image done, and then you can work through it. So my next medical one, this one's close to my heart, no pun intended. My dad had open heart surgery last year, a really scary operation if you know anybody that's gone through it. They actually open up the chest, they give you a drug to stop the heart, Then they have you on a bypass machine so the blood keeps circulating. If that wasn't dangerous in itself, a lot of times the heart just won't restart. They give it the drug to say go, and it just doesn't start. For this reason, most surgeons won't even do open heart surgery unless it's like an absolute life or death situation. There are a few surgeons that will operate on a beating heart. They'll actually go in there while the heart's still going and try to operate. This is where one of the doctors yelled at me. There's something about 80% of the surgeons can operate on a beating heart, but only about 2% of them will, just because it's so hard and so dangerous. And so to help combine the best of both worlds, this is a group that's, what you're looking at here is there's actually two cameras looking in, so in stereo, and it's superimposing this grid you see on this heart here. And from that, they would present the surgeon with this virtually still image on the right. You can see this is actually moving. You can see the light kind of move in, but from most part, it's stopped. And so the surgeon wouldn't actually operate on the heart directly. There's this robot that sits over it, and it's got these 6 arms. And the other nice thing about this is they don't actually open up the chest for this. They just drill 6 little holes in. And as the surgeon makes an incision or puts a stent in or whatever, the robot is actually moving with the beat of the heart and motion compensating and to do the cut and everything. So the heart is still beating. They don't have to stop the heart, but the surgeon gets to work on a still heart. So he actually gets to virtually operate on a still heart. So really important stuff. It's going to help a lot of people in the future. This is currently not in human trials yet. This is actually a pig heart. They're hoping in about 3 years to get this going and actually start their human trials. But really cool stuff. Would not be possible without, on a CPU-based, you'd have to have a supercomputer, and those just don't, you don't have those sitting next to operating rooms. Whereas this is just a fairly powerful GPU workstation you could put underneath the table. Obviously with some redundancy because you wouldn't want to break down in the middle of the surgery. And then finally, I just like this. This is an N-body. I assume everybody knows what N-body is. You have some X number of particles. They interact with each other somehow, and you want to see what happens over time with the system, whether it's gravitational, mechanical, electrical, whatever, what be it. So this is just the CPU versus GPU, an optimized version of the CPU code on the left and then the GPU on the right. And just showing again that using the right processor for the job. You can think this is just an n-squared algorithm. You have 2 for loops where every particle has to figure out how every other particle is affecting it, updates the position, and then redraws the frame. Now on the GPU, you have thousands of threads that can do this all in parallel with each other. It's fairly basic operations, but you just have a lot of them to do. And so this is all part of our SDK, so you're welcome to go out and play with it if you want. But again, it's just using the right processor for the job. GPU would not be able to do this without the CPU. Again, it's running the operating system, it's feeding it the data, it's telling it how to launch the work. So this is one of those hour wasters. You go in and start tweaking little values, and before you know it, 5 hours have gone by. So that's N-body. So where are we at in the supercomputer world? This is actually an older graph, is now dated. There's 2 more in front of it. This is from the top 500 supercomputer list. Green is powered by GPUs as the central processing, and then blue is the CPUs. The 2 out here, there's one in Japan, I can't remember the name, which is CPU-based, and then there's, I think, the new Blue Gene one out here. They're both CPU-based. What we, later this year, early next year, is the new top one will be Titan out in, I'm blanking. Okay, thank you. It'll be Titan. It's supposed to be about a 20 petaflop computer. It'll be the new supercomputer. Basically, supercomputers have become the new space race. It's the who get the fast, which country get the fastest. Because I know when China came out with this one, even Obama got involved, and a lot of the government officials got involved. They got freaked out that now China had all this power as far as supercomputing goes. But what I really like is this graph, superimposed with power consumed. You can see the CPU ones use a lot of power. I mean, this is something like 60,000 homes to power one of these things. Each megawatt is about 10,000 homes. So you see GPUs are very efficient at what they do. Whereas the CPUs, they just have to crank those clocks up, push as much power as they can to get them to go as fast as they can. If there's another list called the top 500 greenest supercomputers, and GPUs dominate that one because they are just really good at what they do, very efficient. Especially with the Kepler family, that was our goal. That was like our soul of the chip, was perf per watt. Perf is no longer the king, it's perf per watt, because we are power limited, whether you're in a mobile device or a supercomputer. I mean, that's why if you notice, these things are always built either near dams or nuclear reactors, because you need that much power to drive these things. So I give this speech a lot to undergrads, so I get in my soapbox here and talk about learning parallel computing, so we'll just skip about this. Mobile space, just as important. If you look, Qualcomm, TI, all these companies are starting to hire parallel programmers, because they have these fairly powerful GPUs, and they don't want them just sitting there idle all the time. Because if you crank the clocks on a CPU, you get a next generation tablet running way hotter than a previous generation tablet. I won't say what tablet this is. Because to do this, they just cranked the clocks up to get more performance, but then they had to put a bigger battery in and have more thermal that they had to get rid of. So it's about being efficient and using the right processor for the job. So you need to be ready, blah, blah, blah. All right, so this is the new Moore's Law. computers aren't getting faster. For 40 years, we used to be able to write our code, at least as a software guy, I used to be able to write my code and just wait. If it didn't run fast enough, a new CPU would come out in a year or so, and it would be fast enough, hopefully. Write my paper, publish it, and then hope it gets faster. We just can't rely on that anymore, because as new CPUs come out, the code's just not going to run faster unless you've written it correctly. So computers are getting wider, not faster. We have to start thinking in parallel. As Microsoft would have you believe, 95% of the world's programmers are VBA programmers. Of those, probably about 90% of those don't know how to write parallel code, whether it's a few threads on their CPU or thousands and thousands of threads on a GPU. So there's very few people that actually know how to write this code, and we're seeing this in the industry. I gave a talk at Mayo Clinic a few months ago, and they were doing a lot of the CT scan type stuff. Really smart PhD computer scientists, and they were having to learn everything from scratch because they came out of school with, they had this amazing toolbox of sequential serial tools in their head. They knew how to attack algorithms. They knew how to, code the various things they needed to get it coded, but they didn't have parallel toolbox. They kind of knew OpenMP, but how do you tie OpenMP with, all of a sudden you have an accelerator with thousands of threads, and then you have 4 of those in a node, and so it's something we need to really make sure we start teaching in school. So as these undergrads and grads come out, people know how to think in parallel, whether you're using CUDA, NVIDIA GPUs, Intel mic, whatever it is. We need to start teaching this. And the best way to think about it is data parallel, because we're always going to have more data. Majority of our problems are just massively data bound. So adding another processor so it can just handle another chunk of data, and your aggregate throughput goes faster. So this is the new Moore's law. All right, any questions so far? I'm going to jump into some technical stuff now. We're going pretty fast. All right. So CUDA by the numbers. Pretty much any NVIDIA GPU sold in the last 6 years, since January 2006, is CUDA capable. Obviously, the newer generations have more features available to them, but there's a lot of them out there. We sell about 100 million GPUs a week. It's about 100 a minute. This is one of the reasons this has driven this innovation. Parallelism did exist before. Actually, back in the late 70s, 80s, 90s, parallelism was having its heyday. So there's a lot of good papers written back there. So if you're doing research, don't throw them out just because they're old. There's obviously some papers that aren't any good anymore, but a lot of them are still very relevant. And what happened was in the late 90s, early 2000s, there was a lot of these really high-end, expensive parallel machines, very custom-made, but very, very expensive. So very few people had access to them. And some, grads didn't have a lot of money, realized, hey, I can go to Best Buy and buy a bunch of white boxes, throw them on a baker's rack in a closet, and now I have a Beowulf cluster that's more powerful than this high-end, expensive machine. And so, economies of scale really killed this parallelism in the late 90s, early 2000s, and it took a big hit because Intel was selling their CPUs to your grandma and to your cousin, and so they had all this money come in to invest in R&D and to keep pushing their CPUs faster. Well, this is what's happened with GPUs now. GPUs were driven by gaming, and so we do have all this research money come in, and we have the competition to keep driving them faster and faster. And like I said, 100 GPUs a minute being sold, that's a lot of R&D dollars to go into this. 1,000 toolkit downloads, this is what you actually need to run CUDA. A lot of active developers. We're now, this number is actually getting pretty old, over 500 universities that have some sort of CUDA course, or they use it for parallel programming. And then roughly about 98 toolkits downloads an hour. It's a marketing slide if you can't tell. So actually, how do you actually code? How do you actually program an NVIDIA GPU? We have 3 ways. Most people think of CUDA as the actual programming language, where you go in and you write C or C++ or Python. Does give you the maximum flexibility. You can tweak the code to your heart's content to get them, pull every perf that you can out of it, but it's hard and it takes a lot of effort. The next step up we have is called OpenACC. I assume you all know OpenMP. This is basically a subgroup of OpenMP. They originally tried to get this added to OpenMP, but it was just taking forever because it's an open standard with lots of people, and a lot of them don't care about accelerators or GPUs. So for now, they've broken off into a separate standard. The president of OpenMP is all for it. The plan is to eventually roll this back in, so it'll just be one standard, OpenMP, backwards compatible, of course. All the members of this open standard are members of OpenMP as well. But essentially, this is just compiler directives, just like OpenMP. You put some few hints around your for loops, maybe tell it a little bit about the data, so it's not, because you can actually add some hints that slow things down because it doesn't know how to handle the data. But again, just a few lines of code and you can get a lot of speed up. For a lot of people, that's enough speed up for them. It's good enough for the work they're doing. It's also a good way to prototype, say, I think I can get speed up here, let the compiler tell me, yes, you can, and then you actually dive into your CUDA code and tweak it so to get the full perf. And then there's the libraries on top of that. Just like MKL libraries, anything, there's tons of libraries out there. I think I have a slide on some of them. Like what we call CUDA sparse, there's CUDA random, if you're doing sparse matrix, any kind of sparse matrix operations, CUBLOS, any kind of basic linear algebra. And there's thousands of libraries out there, fast Fourier transforms. We have hundreds and thousands of image processing things. I think I was talking to you about doing image tracking. There's lots of libraries already out there that if somebody's optimized the code for you, they've written the CUDA code, it's just drop in. So I encourage you, if you are considering doing any kind of work like this, look at your existing code, look at the libraries you call, and see if there's an existing GPU one for you. And then again, it's just you switch the API call and you're done. Most people use a combination of all three of these. The existing code that's already written, don't reinvent the wheel. Use those building blocks. So you drop in the libraries. You use your OpenACC to go in there and see what you can parallelize. And if it's fast enough, you're done. And if not, then you actually get in with CUDA code. We have plenty of success stories with OpenACC, people putting in like 6 hours of work and getting like 5x speed up. And we have this, there's a guy in Australia who spends 99% of his time out in the water working with fish. He's got the big grizzled beard and tan. He does not look like a computer coder at all. And he's had this code for 30 years, some old Fortran code, and it's literally within 6 hours, and I think he did 5 lines of code, and most of that time was just reading the documentation. He got a 5x speed up in his code. And it was because he just had a whole bunch of nested loops, and he let the compiler do the work for him. So you can get plenty of good speed for just a few hours of work here, so I highly encourage you to try this if you were looking to see if your code can run faster. And it supports Fortran and C. Unfortunately, C++ is still in the works. C++ is hard to do this because you have an array of structures instead of structures of arrays, which is really hard for the compiler to figure out. So C++ is being worked on, but it doesn't exist yet. As far as actual commercial implementations of this, there's PGI has one, CAPS has one, and then Cray's coming out one for their actual specific hardware. So for just standard hardware, you'd want to look at CAPS or PGI. Yeah, here's OpenACC Directives. So again, it's just like OpenMP. You put a few hints for the code. The compiler doesn't understand it, it'll just throw it out and ignore it, so you don't have to actually change your underlying code. Although we found by tweaking your underlying code to work better, it'll actually speed up even in the non-parallel case. So it just restructures your code so it's more efficient. So that's OpenACC. As far as actual languages available for CUDA to actually write the CUDA code, there's C, C++, Fortran, Python is coming along. A lot of people are enjoying Python now. .NET. MATLAB is really big in the university space, so it's really easy to do MATLAB. Actually, I think I have a couple slides on that. On the actual MATLAB, their own product, Parallel Computing Toolbox, big speed ups in all these operations, and it's really easy to write. You just, instead of doing an array, you do GPU array, and then all the rest of your code's the same. It handles transferring the data to the device and doing all the work. There's a competing one from Accelerated. We like that there's a competing one because they've been pushing each other really hard to go faster and faster. Right now, I'd say Accelerated is probably the fastest, but MATLAB's pushing pretty hard, and pretty soon they should catch up to them. So that's MATLAB. And then as far as just the tools we have available, we have this tool called Parallel Nsight. This integrates with both Visual Studio and now Eclipse, which makes the Mac and Linux guys very happy. So if you use an Eclipse IDE, this now integrates. And what this Parallel Nsight is it's a visual debugger. You can actually set breakpoints in your CUDA code on your device and source line step through. You can look at an individual thread out of your thousands of threads running, pull out all the variables just like you could on the CPU. We have this great timeline profiling tool. We'll show you, what your CPU is doing, what the API calls are doing, what the mem copies are doing, all over this nice broken out timeline you can zoom in and out of. You can actually go in and it'll show you, your occupancy, how much, cache hits you have, where your bottlenecks are. It'll actually suggest where you can make improvements. So if you're actually writing real CUDA code, if you're not programming at this, you're really hurting yourself because this is a very powerful tool that's just available to use. That's a video Parallel Nsight. All right, so what is CUDA? We'll actually jump into our little CUDA C here. Anybody know what CUDA stands for? Anyone take a guess? Oh, I almost always burn somebody on this question. Unfortunately, like 5-10 years ago, some marketing guy got a hold of the CUDA and they thought it was an acronym. So they said, oh, it's Compute Unified Device Architecture or Driver Architecture. And so we don't know why they put that out. If you think about it, that really doesn't even make any sense. What does that mean? So CUDA is actually not an acronym. Unfortunately, there's a lot of papers published, NVIDIA papers published that state that. But I've triple confirmed with Ian, the guy who invented this, that all CUDA is actually the CUDA car. I don't know if you guys remember the car from way back when. When he wrote Brook, which was his thing at Stanford, he actually had the CUDA car on the cover. And that's why he's like, when they were looking for a name, he's like, oh, let's call it CUDA because that's the car I use. So if you see anybody use as an acronym, feel free to yell at them. Say, Mark Ebersol said. This is not true. So CUDA is just a name, just the name we came up for it. It's basically the way of exposing the parallelism of a GPU. Like I said before, people had to hack OpenGL or DirectX to do this. They were paid a lot of money at the time before CUDA came out because it was very hard. But yeah, it's essentially just a few extensions to C and C++ to expose the parallelism on a GPU. A bit of a confession to make, I've not been a CUDA coder for very long. I was actually a low-level systems guy for quite a while. I couldn't render a triangle to save my life, even though I've been in NVIDIA 6 years now. I was working more on figuring out if the hardware was good or bad and then helping debug it. So I got tired of that. I got tired of debugging silicon issues and dealing with the hardware guys. So I would see these CUDA talks at our software all hands and see the really cool things being done, not just what NVIDIA was doing, but people were doing with our tool. I mean, there's crazy stuff going on. People sending robots to Mars or solving really interesting diseases. Just saw an article today about GPU cluster in the UK, like their big one. They just found some. They were basically looking at trying to guess mutations that would prevent drugs from working in the future, and they found some big breakthrough. But very cool stuff happening with GPUs. And although it was fun having fanboys playing our games that only motivates you for so long, it was actually like giving back to the world. So I guess the point of the story is you don't need to be GPU experienced. You don't know how to do graphics. You don't really need parallel experience, although it helps you to, especially once you start expanding. And then, yeah, you don't need graphics experience. Don't need to be the deer in the headlights. All right, so this is where it gets a bit technical. Feel free to interrupt me. If you get lost early, you'll probably be more lost as we go on. And most likely, if you have a question, everybody else has the same question. This is a pretty basic introduction, but just these 4 concepts we're going to go over. The biggest one I think you need to know is this terminology. Is we have the host, which we call the host as the CPU and its system memory, and then the device, which is the GPU and its memory. And it's important that you recognize that they have 2 different memory spaces. Every CUDA program, every compute program, whether it's AMD, Mike, NVIDIA, all follow the same basic flow. You got to get data to the GPU. Obviously, if you don't have data, there's nothing to do. You do your work, whether it's fast Fourier transforms or a bunch of matrix operations, whatever it is. You kick off the GPU and you let it go, and then you do something with that data. Either copy it back, write it to a file, tell your robot to go write, whatever it is. So that's the basic flow. Now here's SAXPY, standard serial SAXPY. Anybody know what SAXPY stands for? No. Single precision A times X plus Y. Very basic linear algebra algorithm. So you're just taking A times the elements of X plus Y and then storing them back in Y. Doing this for a million elements, very basic. You just go through a for loop. I assume this makes sense to everybody in here. All right, so that's SAXPY. So we're going to parallelize this on the GPU. All right, so before we do that, we need some few concepts, because obviously on a CPU you're dealing with 1 to 8 cores and most likely 1 or a few threads. On a GPU you have thousands and thousands of actual cores available to you. Actually, in our latest it's 1536. And on top of that, you have millions of threads to do the work for you. So we need concepts to help the software guys code this, because it's fairly complicated. So the first one is called the CUDA block. When we actually run something on a GPU, it's called a kernel. I hated that they use this phrase, because I always think kernel is like a Linux kernel, and it's overloaded, but that's what it is. So when you actually launch something on GPU, you hear people call it a kernel. And when this gets launched, it actually gets multiple copies of this are going to run on the GPU at once, and that's called a block. And again, I'm an analogous learner, so I think of a block as a hamster cage. So when you actually launch a kernel on the GPU, it's called a grid, and there are multiple copies of this hamster cage, exact same hamster cage, some number of times. Now, since we don't want each hamster cage we want it to work on its own set of data, because obviously if you repeat data, there's no good to that. Each one of these are able to ID themselves. There's block index up to however many you have. So this is a read-only variable presented to you to identify which cage you're in. Now, so different grid is different size cages, different code. These can all run in parallel, simultaneous on the GPU. All these blocks are independent. Now, within a block, you have what are called threads. These are what actually do the work. And if you see where this analogy is going, a thread is like a hamster. So the hamster is what actually does the work. And there's a whole bunch of them that live within a block. Now, within a block, hamsters can talk to each other. They can synchronize. They can share data. They're all a little happy in their little cage. And again, they need to identify themselves. Obviously, they want to make sure they work on their right data. So there's a variable called thread index, again, defined for you. You just read it. And this is how the hamsters know what piece of data to work on. And another useful one we'll use a little later is the block dimension. That just shows you how many hamsters are in a cage. So that's threads and blocks. So again, why do we do this? So threads within a block, again, can communicate. They can synchronize. They can they can share data. So then I get the question, well, why don't we just have one giant block with all the hamsters in that one cage? That's partly hardware-based. We have basically one block can fit into an SM, which is our streaming multiprocessor. This also allows the hardware to schedule blocks as it sees fit. So for instance, if you had a GPU that could only do 2 blocks at a time, it would take you 4 time steps to do your code. But then if you just later move your code to a faster GPU, it goes a lot faster because it can handle more blocks at once. And again, if you're say you're playing a game, Some of those blocks will be physics-based. They're doing the physics works, and some of them will be, graphics-based. They're actually rendering it. The hardware can schedule it however they want because these blocks are independent of each other. They can't talk. They can't synchronize. You have no idea which order they're going to go in. That's why we do blocks. Just to give you, to map it from the software perspective down to actual hardware, this is the chip that's being passed around, Kepler GK110. Each one of these, so the whole thing is a grid. When you launch something, it's running on the whole GPU called a grid. And then each hamster cage, each block, it maps to these SMs. And on that GK110, there's 15 of these SMs. Basically all identical. That's why we did it that way. So you just stamp down as many as you have room for silicon. If some of these are bad, you can actually floor sweep them out, and you still have a workable chip, just not as fast. And then the actual hamsters, the threads, they map to these little individual green dots. This is the actual, basically an ALU. That's a CUDA core, or as we call it, a core. That's what does the work. Each one of these SMs have 192, so now that's why we have 1536 of these in GK110. And you see these orange ones on the side. These are actually double precision. We now have 64 of these in GK110, which has given us a really big boost in our double precision performance over our previous generations. So now I think we're like 3x more powerful than our last high-end Fermi GPU. And then we also have some special function units down here that do, sine, cosine. There's hardware versions of these that are very fast. They're not quite as precise as doing them, actually doing a software version in the cores, but they're very fast. So that's how they map. So the grid is the whole thing. The blocks are the S per SM, and you can have 8 blocks at once active in an SM, and then where the hamsters or the threads actually do their work are on these little cores. Make sense, everybody? We good so far? All right. So let's actually parallelize our code, and this is actually it. That's nothing very exciting. First thing you'll notice is this new global thing, keyword we've added to the C language. This essentially just tells the compiler this is something that'll run on the device, and it's callable from the host. So that's all you need to say, hey, this is a GPU function. The next thing you notice is our for loop is gone. All right, we no longer have a for loop, so now we need I to go from 0 to however many elements we have. And so to do that, we use these 3 variables I talked about. We first figure out what hamster cage, which block we're in. We figure out how many threads we have, and then we add our thread IDs. So if you've ever done any 2D to one-dimensional mapping, this is exactly what's going on here. So that gives us I, and I'll run through an example here that'll make more sense. So once we have our I, we need to actually do our work. And people ask, well, why do we have this I less than n? Well, just like the for loop, we had to stop at some point. You don't want to do more work than you have data, because otherwise you start overwriting memory, and nobody's happy. So there's a good chance you will have a block that has, majority of the hamsters have some work to do, but there's some hamster at the end who's just there for fun. He got stuck in the cage because you always have the same number of hamsters per cage, but you need to make sure he's not doing any real work. So let's run through an example. We're just going to do 30 data elements, very basic. I arbitrarily broke this up. I'm going to use 3 blocks or 3 hamster cages and then 10 hamsters per cage to do this work. So block dimension's 10. So now to get I from 0 to 9, our first block is going to have a block ID of 0, times 10 plus our thread. So this gives me an I from 0 to 9. And you have to realize code is being run in parallel by many, many threads. So the for loop is essentially kind of done by the hardware outside of your code. It's just launching this thousands of copies of this code at once and it's just tweaking these variables so you know which data to work on. So in the next case, we will have a block running on a different SM, most likely, with a block ID 1, times 10. So this is how we get I to go from 10 to 19, and then finally from 20 to 29. Make sense? All right. So that's our code. How do we actually launch it? What's our main look like? This is the same code on both sides to start with, just basic serial code. We're going to do 1 million elements. We have our host pointers, how big our data is, and we initialize it. Just like our process flow I showed you a little earlier, the first thing we have to do is since we have a separate memory space, we need separate pointers. We need to allocate space, just like your standard malloc, just called CUDA malloc. This is part of our runtime API. But yeah, just your pointer and your size. And then we initialize our data. Now we need to get the data to the GPU. So we use CUDA memcopy, again, very similar to memcopy. The only difference here is we now have this extra parameter at the end that says which direction the data is going, whether going from device to host, host to device, device to device. And now we actually launch our work. So in this case, this is another new thing we've added to the language, these triple angle brackets. This is how we actually specify our launch parameters. In this case, we're saying how many blocks we want and then how many threads per block. So this obviously, this case is a little arbitrary because I hard-coded it to equal 1 million elements. But usually in practice, what you'll do is through tweaking of your code and experiments, you'll figure out the optimal threads per block, and you'll hard code that. And then based on your data, you'll figure out how many blocks you actually need to cover to do your whole data set. And obviously, you want one enough to cover everything, but you don't want to be one short, so you're missing some data. But that's all it takes to actually launch a kernel on the GPU, and then just passing your parameters. Question?
So that step is an experimental process?
Yeah, usually figuring out the number of threads you need is very dependent on your problem. Problems are very different. Sometimes having one, as I call them, really fat hamsters that have consume lots of registers and lots of shared memory is better because they're not going to global memory as much, or it really depends on the problem. Whereas other times having really skinny hamsters so you can have a whole bunch of them all working at once is a better option. There's a lot of papers still being written on this. So there's actually tools out there that will just automatically try to figure this out for you. In practice, between 128 and 256 threads we find is optimal, somewhere in that range.
Well, one statement I saw reading third-party authors about this was that you have to sculpt your algorithm to match the hardware.
To a degree, yes.
And I never was clear on what that meant. And I inferred that I guess that what it meant was you looked at how many, you looked at the SMs, you looked at the number of SMs, and somehow you're mapping into the SMs, and you have to know the number of SMs that are collected together. And I wondered if that was a more deterministic way of getting into the best performance. But you're saying it's experimentation with those.
Again, it's some experimentation and knowing your hardware. Again, like you were saying, depending on the hardware you're on, if you really want to tune, it'll vary from generation to generation. A lot of the problems is not the number of SMs, it's the number of registers you have available in each SM, and the number of shared memory, which is basically user-controlled cache you have available. Because if you're not careful, you start getting into register spilling, and so the register spills out into global memory, which you go from 1 cycle to read the register to 800 cycles to read that register because you spilled out. So it's not really how many SMs you have, because SMs are all identical. The more you have, just the faster you're going to go. It's more what's inside of the SM, how many cores you have, how many registers you have available. And when they're talking about tuning your algorithm, an algorithm that works really well on the CPU is not going to work well on the GPU. Most of your algorithms on the CPU are used to working with a CPU cache, and having a single thread access stuff sequentially is very fast in a CPU. In a GPU, that's the worst thing you can do, because that means a single thread is accessing 1 byte from each cache line, and that's a lot of operations at once. So you want, getting a little more technical, things are actually launched in what are called warps, 32 threads at a time. And each one of those warps is basically a SIMD, a single instruction, multiple data. So each thread in that warp will execute the exact same instruction. So what you want is each warp to access a single cache line. And so when they're saying structuring, it's changing, it's stuff like that. Having threads access data sequentially. Each thread will access a piece of data, then its neighbor accesses the data right next to it, because that's how it reads it in. And so that's what they most likely mean structuring your algorithm for the GPU. And again, then when you actually get into the SM, it's how many registers you have, how many you're using, how much shared memory you're using, because it's tuning for the hardware. And then figuring that all feeds into actually how many threads you have. Yep. But there's still a lot of papers being written on this. Hopefully in 5-10 years this will just go away. Then the compilers will be far enough along. But
looking for a more deterministic way to.
Yeah, and this is where OpenACC will does all this for you. It tries to figure all this out for you. You can go in and tell it if it's not working fast enough for you. You can help specify, but it, as a compiler, tries to figure out these numbers for you. So again, this is actually when you want to get down and dirty and do all the work yourself. And then again, copy data back, and since we're good coders, we free up our memory. So that's a CUDA program, very basic. Obviously, you wouldn't run this by itself because you're transferring. You're sending a lot of data back and forth across the PEX to do very simple operations, but this is kind of just an example to show you how to actually write CUDA. Again, probably the biggest bottleneck in this system is the PEX bus, transferring the data back and forth. Then after that, it's reading data from the global memory, from the DRAM of a chip. Again, data movement is the most costly, whether you're a CPU or a GPU. You want to get your data local really as quick as you can, and keep it there as long as you can to actually do your work. So any questions? That was actually it. That was your first CUDA program. Question?
So you made a comment
Yep.
at the end there that this is not, you wouldn't actually do this example. This is.
I wouldn't do just this.
Where's the trade-off here? I mean, suppose you were to do just this. How much data would you have to, how big would the problem have to be in order for it to be more efficient?
It would probably never be more efficient because you're doing 3 copies for one operation. Yeah, you're transferring way more bytes than you're doing operations. So, but what would this be useful is if you already had the data on the GPU, you transfer it there, you're doing matrix operations, and you're doing SAXP, then you're doing Fourier transforms. All that data is already over there, and so that aggregate's going to be much faster overall than just doing all the transfer, a little bit of operation, and all the transfer back. So yeah, data movement's very costly. Okay, any other questions? All right. Just now to go into a few more examples of people actually using CUDA today. Reed Siebert, I love this quote because when I first read it, I just assumed he's one of our fanboys. That we can give him the crappiest card in the world, and they'll get tattoos and name their kids NVIDIA and stuff. But no, he's very active in our forums. He's one of the most active in our forums, and he's the first one to say, when AMD comes out with a better part, or if OpenCL works better, I'm going to jump ship immediately because I just care about perf and being in ease of programming. But his problem was, as he was doing this stuff, which I don't understand at all, in his thesis, he was finding on the computers he had available that it just wasn't going to finish in time to get his thesis in. So he had to find another solution. And that's when he, this was a couple years ago, found OpenCL, or found CUDA, found the NVIDIA GPUs, and was able to actually quickly write it up and get his stuff done much faster than the computers he had available to him, and actually finish his thesis in time. Professor Barbara, you all know the algorithms book. Every school uses that thick algorithms book that's been around for like 40 years. Basically saying that these are the best algorithms to use for various things. She's making part of her career out of taking those algorithms and proving a lot of those are no longer true. Like quicksort's no longer the fastest way in general to sort something. There's faster ways on the GPUs to do it. The problem is when that book was written, parallelism wasn't very big. Even if those machines were there, they weren't overly fast. Now we have these extremely fast GPUs. So she's just taking CUDA, taking all these older algorithms and coming up with better ways to do them. As I'll talk about later in my second talk, that algorithms book for parallel computing hasn't been written yet. That book really needs to be written because the algorithms book is used everywhere. Ian Kuzin, professor at Purdue, one of my favorite guys. He's really fun to listen and talk to. He's been interviewed CNN, Science Times, and he has the nickname the Locust Whisperer. So he basically studies swarms, and he does this with n-body systems. And he loves GPUs and CUDAs because, as we saw, they're very good at n-body stuff. One of my favorite examples are he studies ants, like those big ant colonies in South America. Like, how do they find food, first of all? And once they find food, these are the ants that will kill a human or a cow or whatever it is. Every time they find food, they form these really efficient 5-lane highways. There's 3 lanes of ants going out to the food, 2 lanes carrying the food back, and then they get flanked by army ants, like every time. And how does that work? Like, he wants to know, how does that suddenly appear? Because when you look at an ant, they're stupid. These are tiny little dumb creatures. There's no brains to them at all. And it's not like the Queen's broadcasting messages saying, controlling all these things, telling them where to go. So how does this work? And then at this point, I usually get asked, well, why do we care? Who cares about what the ants do? And like one application is like, think of the packets in the internet. Imagine if each packet was like an ant. Now if like one of the domain controllers go down, who cares? The packets know what they're doing because they're not getting instructed of where to go. But he was able to come up with a set of rules, something like 10 to 15 rules in his virtual world, and actually simulate what was happening in the real world. Basically if an ant runs into this stimulus, drop this scent, or if it runs into this scent, do this. And through that, he was able to model what was going on. Another cool one is the locust, where he got his name, the Locust Whisperer, is to figure out why locusts were swarming. Why does it happen every few years, and why do they just destroy crops? What's going on? And what's happening is that the locusts actually get really hungry, and then one gets the bright idea that he's just going to eat the other locust next to him. And so he goes and starts eating that guy. Then all the other locusts say, hey, that looks good. I'm hungry too. So they all just start trying to eat each other, basically. So it's a big mass of trying to avoid being eaten and trying to eat the guy in front of you because you're hungry. And of course, when they land on a field, they're all in this frenzy mode, so they just devour the field. So through that, they're able to study more likely when it's going to happen, how to prevent it. Just very useful stuff being done today with GPUs and CUDA. Back to your image recognition one, I always like this example because it's really cool from a technology standpoint, but it kind of scares me. So this is just people walking down the hall, and then in real time, it's doing facial recognition, first finding a face, and then once it finds it, it's comparing it against their badge picture and figuring out who they are. This creeps me out at work because I know there's cameras everywhere. That's very easy for my boss to track me where I am. It's all being done on one GPU, or it's a workstation GPUs, but both the image recognition, this guy always creeps me out because he looks at the camera. I don't know why every time. But it's doing both image recognition and the comparison on the GPU. Again, those are just massively parallel problems what the GPU is very good at doing. And then my favorite demo to end with, I'm from Minnesota. I hate mosquitoes. I apologize if anybody here likes mosquitoes. This is a project to fight malaria in third world countries. There's a really good TED Talk on this if I encourage you to go watch it if this interests you. But what they would do is they put posts around either the village or the hospital, whatever it is. And between each post, they have a very low power laser grid. And anytime anything breaks the laser grid, they want to see what it is. So they have webcams that are doing image recognition. And they can, A, detect that it was a mosquito that broke the grid, and B, that was actually a female mosquito, because they're the only ones that bite people. And they do that based on the beat of the wings, speed, and the size, because they're a little bit bigger. Now, once they've detected it's a mosquito, they actually use a more powerful laser and shoot it down in real time. And that's what you're seeing going on here. This is slow motion. Because they actually, and you only have to, you just briefly have to hit them. They die almost instantly. The wings melting off is just a bonus, but they're already dead at this point. And since this is third world countries, it has to be efficient and cheap. So for the image processing and the targeting of the laser, they're using our old G80s, one of our first GPUs that are CUDA capable, because nobody wants those anymore. You just find them sitting around. But they're also very efficient again. They don't have power out to these villages, so they got to run on battery during the night and solar power during the day. And it's all off-the-shelf components. The laser that's actually shooting them is just a Blu-ray laser from a Blu-ray player. The control to actually control the lasers from a laser printer. They actually pulled out the electronics from there. And then just webcams, and it's really cool. It's one of my favorite uses of GPUs that I've definitely seen. But yeah, the TED Talk's really interesting. They actually have mosquitoes in a little box on stage, and they're lighting them up with a low-power laser, so you can actually.
It's actually burning a lowercase a onto that. So how big a device is that?
It's actually pretty small. I think it sits on top of a pole like this, and then there's a laser that's bouncing back and forth.
Mosquitoes to go through it, right?
Well, they don't. Mosquitoes only fly so high, so you just had to get it. It's up to like 12 feet or something, and then basically it's just to keep them out, right? To date, all they had were nets was the only really solution. So this is something they're trying. I know they have it in a number of places, but all right. So this is kind of the end of my first talk. Again, if you're interested, go to Get CUDA. I think this is up. I don't know if you all know we got hacked pretty hard, so a lot of our site is still down. Yeah, they got same people. We think it's the same people that did LinkedIn and Yahoo and all those companies. So yeah, we got hit pretty hard too. But the question I ask is, what would you do with 10 to 100x speed up? I mean, this is what we realistically see. Hundreds on the high end, obviously, but easily 5 to 15x speed up in a lot of the existing codes out there. What could you do with that? What bigger problems could you go after? This is more for the undergrads that I talk to. Obviously, if you are working on cool stuff, please let me know. We spotlight people all the time, put papers up. We do have this thing I know interested a lot of the researchers called GPU Test Drive. It's just I think it's a petaflop cluster we run. Has a lot of existing codes on it, like NAMD, Amber, all these. But we also allow you to upload your code. You just have to go register and tell us what you're going to do, and then we give you some time, and you can go see if you can get speed up. This way you don't actually have to buy the equipment. You don't have to get somebody to set it up. We're running it for you. So this is a great way to actually go out and test drive something. And then I usually give out 480s. I have a couple I'll give to somebody here. So if you just send me an email with some CUDA code, I'll do a drawing and hand them out. We have a few number of these. I like to get rid of them because that's a couple generations old, but it's still a pretty powerful CUDA device. So please feel free to send me an email and I'll do the drawing. Here's my email. Nobody remembers my name, so you can just email CUDA Hamster because most people remember that after my talk. All right, well, that's the end of my first presentation. Any questions? Feel free to take 5 minutes, go to the bathroom.
So this is, you can also use, like if you have a NVIDIA graphics card for your computer, you can talk to its GPU?
Yeah, like I write most of my code on my laptop. And now we are, I talk about in the next slide, but we're back in the Mac. So if you're interested in buying a new Mac laptop, we now have our Kepler, so one of our newest chips in there. We were out for a while because our Fermis, although powerful, weren't very perf per watt efficient, and Apple said, oh, you're out, because they're very, rightfully so, it wasn't a great experience, but we attacked that. Now we're very perf per watt efficient, so we're back in the Mac. That's a good way to do development. Yep.
Given the examples you used from the researchers, do you have any idea what hardware configuration they're using in their research?
Not off the top of my head, no. I mean, I could pull up the papers and look. Majority of like the molecular, people actually doing like real big clusters are Tesla class Fermi stuff. So they don't even have display out. They're just purely meant for computing. Most likely the one you saw, like the facial recognition, that's usually lower end cards because universities don't have a lot of money to go buy. Especially if the undergrads will just play with like 2 or 3 GPUs, so they'll use like a gaming card, like what we call as GeForces. GeForce is our gaming brand. They're very powerful, but they're not nearly as well tested as our Tesla ones. Like a GeForce one will have like 5 minutes of testing after it's built just to make sure it's good, whereas like a Tesla one goes through like a 24-hour burn-in to make sure all the memory's good, make sure everything's high quality, because obviously you don't want bits flipping on you in the middle of your research. But yeah, any GPU, like I said, in the last 5 years can actually run CUDA. So, okay. Yep.
Float to double ratio.
Float to double ratio, what do you mean?
Single position to double position ratio.
Well, on the GK110, there's 192 single precision cores and 64 double precisions per. Yeah, but that's a lot better than it was before. I think the previous generation had 8 double precision cores per SM.
Yeah, because I have one of those, like C1068,
Mm-hmm.
over in that lab, and tried that from the version
Yeah, so with GK110, we've really targeted compute with that chip. Before, like our previous GTX 680, the first chips coming out in Kepler they're gaming cards. I mean, people complain they're not very double precision speed up, but I mean, that's a gaming card. It wasn't meant to be. It runs compute very well, but that's not what it was targeted at. Our GK110 is really our high performance computing answer, and that's 3x perf per watt or perf over our previous generation. Plus, it runs at a lot less power. So yeah, that's the card you want to get if you need double precision.
So in real world code, what is the kind of breakdown between single precision code and double precision code?
A lot of the like oil and gas.
Computing and not gaming.
Yeah, a lot of oil, gas, image processing are all single precision. Then when you get into the more like molecular kind of codes, bioinformatics and stuff, that's a lot more double precision based. So it really depends on the application you're working on. A lot of people don't need that much double precision. They don't need that precision, and so that just slows everything down, so they can get by with single precision. But so it's really just it depends on the industry. I don't know if I can give you a good actual breakdown percentage of what's used out there, because we don't really even know how many people, what people are using our stuff for, in general. Does that answer your question? Yeah, I mean, we obviously know people want double precision. That's why we really put a lot into this new chip, because people need that double precision capability. Okay. Anything else? Yep.
So you mentioned, I believe you mentioned that some blocks, each block does the same job, but different blocks can do different jobs, right?
So each block is the same copy of the code, but it will have a different block ID.
Right, so you can have certain blocks just working for graphics,
Yeah.
while others work for...
So the SM doesn't care. It'll have 8 active blocks at a time. They can be from any grid. You could have 8 different grids running on it. It could be 8 of the same grid. Yeah, the SM doesn't care, because they're completely independent entities. They don't talk to each other. They don't rely on each other.
So if you have one GPU and you're doing CUDA programming on it, and your program has some error, like infinite looping or any bug,
Yes,
it doesn't affect your graphics?
it can, yeah. Currently today, they're not good at multitasking. It's easy to screw up everything else that's running on there. You could run an infinite for loop that just consumes all the bandwidth, and it will slow everything else down. That is still very possible on a GPU today.
But it won't affect other blocks. It won't affect the blocks that are responsible.
It will, because if you have an infinite loop, it's basically going to stay on the SM forever, so other blocks don't get a chance to come in and do work. So they'll most likely trickle through, but it'll be very slow. Because there's no priority. You can't set something's a higher priority than the others. It's all, the hardware is just going to go through and do it like a nice fair round robin. And if one's just sitting on there forever, it just never gets evicted, and it's just consuming cycles. Yeah, we don't have preemption on GPUs today. It's something we're investing in, but it doesn't exist today. So that's virtualizing compute on a GPU is still pretty tough. There's some work stealing algorithms that have been written, but it's more software-based than hardware-based.
The best way of doing it is having a GPU for graphics and another GPU for programming.
Or just write your code better.
Yeah.
No, I mean, yeah, that's because today we routinely run physics and graphics all the time. And obviously, if we have a bug like in our physics or our graphics, we're going to catch it pretty quick. But yeah, if you have people sharing a GPU, that's where you can get into trouble. And that's just where it is. Okay. All right, well, let's take a break. You can, yeah.